Welcome to In 5 Minutes. The agenda of this clip is to understand the concept of clock skew. On the screen, I've just presumed that this is an IC, let's say, which has a lot of blocks inside it, which is unit 1, unit 2, unit 3, unit 4, so on and so forth. And I have shown here that this is my external clock, and the clock going to unit 1, unit 2, unit 3 are called phi 1, phi 2, phi 3 respectively, and the length of the clock, or the length of the interconnect to be more precise, is L1, L2 and L3 respectively. Now let's understand what is clock skew and how is it different from clock jitter. In the previous clip we have already studied that the delay is given by R line into C line. We have already done this. In case you need to refer, go back and refer to a previous clip. And we have also said that R line into C line is nothing but B into L square, where B is equal to small rc, which is a constant for line with units of second by centimeter square. So this relation tells me very clearly that my delay is proportional to or directly proportional to length square or L square, which means that as the interconnect length keeps on increasing, my delay will keep on increasing. Here we have shown on the diagram that unit 1 is getting its clock signal by an interconnect of length L1, unit 2 is getting its clock signal by an interconnect of length L2, so on and so forth. Now what we need to understand is, I have drawn here on the graph or on the waveform, when does unit 1, unit 2 and other units receive their respective clocks, and I have called their clocks as phi 1, phi 2, so on and so forth. So let's presume as an example that phi 1 gets its clock like this. Now if you see from the diagram, you can easily make out that L2, see the path, L2 is surely greater than L1. That means delay of the clock to reach unit 2 would be more than delay of the clock to reach unit 1. So this difference in the time between the clock, or I would make it very simple, this difference in the time at the two receiver points at which the clock is received is nothing but clock skew. I repeat, let's take an example that unit 1 receives its clock at 2 nanoseconds, unit 2 receives its clock at 4 nanoseconds, unit 3 receives its clock at 6 nanoseconds. Technically all of them should receive at 2 nanoseconds only, because it's a synchronized circuit and all of them, let's presume that they are all flip-flops or registers, we want all of them to operate or become transparent if they are positive edge triggered or negative edge triggered at the same edge. But because of the clock skew, which here we saw that because of the length of the interconnect, which is varying from unit to unit, one unit will receive its clock at say X time, the other unit might receive its clock at X plus some time. This difference at the receiver end or at the receiver points when the clock is received is nothing but clock skew. So if we presume this is unit 2 and the length or L2 is greater than L1, that means compared to unit 1, L2 will receive its clock slightly late. So this is nothing but delta T1. The difference is nothing but T2 minus T1, the time taken by the clock to receive block 2 minus the time taken by the clock to go to unit 1. And we know that T2 is nothing but BL2 square because it's unit 2, right? So it will depend on the length of its interconnect. T1 will depend on the length of its interconnect. And this is nothing but L2 square minus L1 square. That is the difference. And this difference is nothing but clock skew. So another important thing which you can make out from the waveform is clock skew will delay the arrival of clock depending on the length of the interconnect. That means the phase of my clock 2 or unit 2's clock will vary compared to the phase of my unit 1 clock. That means if this was going high here, this is getting delayed, the phase variation happens. However, if you see the clock period, right, or the frequency, the clock period remains the same. There is no variation in the clock period or the clock frequency. The only thing which varies is the phase. Let's understand this in respect to the diagram which we drew for clock jitter. So here was a diagram which we drew at that point of time. This was my flip-flop 1, this was my flip-flop 2, this was my combination block, and we've said that this was time equal to 0 and this was time equal to t, and the clock source had to give its clock at time equal to 0 and time equal to t. But that was, we were assuming idle clocks. In practical scenario, what happens is this clock source needs to drive, or the clock needs to go to a lot of blocks. We know that there are millions of transistors on an IC, right? So there are a lot of blocks where this clock needs to go. And hence we know that the concept of repeaters or buffers are added in the path to restore the signal strength or restore the value of the signal. And also that if we break the wire or the interconnect by adding repeaters, suppose this was my interconnect of 100 meters, then my delay would be 100 square. If I break it into two parts by adding a repeater in between and say that first interconnect is 50 and the other interconnect is also 50 meters, then it will be 50 square plus 50 square, which would surely be less than 100 square. This is just for your reference, guys. What I'm trying to bring to your notice is the clock does not get directly connected to all the blocks. It needs to be passed through a buffer chain or driver trees, etc, etc. In this case, my clock 1 will come after the clock is ready plus T1 plus T2 time. Let's say T1 is the time taken by this buffer, T2 is the time taken by this buffer. Whereas my clock 2 will come after the clock is ready, T1, it comes in its part, T3 and T4. So this is for clock 2. So this difference in time between this two is nothing but clock skew. Now we saw that clock skew varies the phase of my clock, but it does not alter my frequency or the period, which we just saw. And this variation of the phase happens due to primarily two reasons. One is the interconnects. We saw that it's proportional to L square. So one is the interconnect length, and the other one is because of the buffers, which will also add to the delay on the path. Though we saw that it will reduce the length of the interconnect, but buffer itself will have its own delays. So these are the two reasons why the variation in phase happens, but there is no change in the frequency. The other point which we need to understand is that clock skew can be positive or negative. Now it's very common. If my clock source is taken in this direction, then we know that T2 minus T1 would be positive. If my clock source would have been in this direction, then T2 would have received its clock first, or the block 1 or clock 1 would have been received late, and still if we consider the skew as T2 minus T1, then the sign would change. So clock skew would be positive or negative depending on the position of your clock source, if it's here or here, depending on the positions of your blocks as well, and which way you are routing your signal. Again, it's very common sense. If you are getting confused, this is my block and this is my clock source, and if I want to take the difference between T2 minus T1, it will be a positive value. If my clock source is here, this will come first and this will come second, but because I want to take a difference of second and first this way only, this would be a negative value. It just shows how are you going to route your wires, or how are you going to place your clock source. In simple words, what you need to remember is clock skew can be positive or negative. Clock skew varies the phase but does not change the frequency or the period of my signal. And very important is clock skew is constant from cycle to cycle. Remember, in clock jitter, it was temporary variation of the clock period. Sometimes the clock period could be less than t, sometimes the clock period could be greater than t, so on and so forth, and keeps on varying for each cycle. Whereas clock skew, because it does not alter the frequency or period, it is constant from cycle to cycle. In simple words, it says that if clock 2 has lagged clock 1 by delta in the first clock cycle, and then on next all the cycles it will lag by the same amount. This can be easily seen from this waveform also. There is no alteration in the lag which was in the first cycle or in the second cycle for nth cycle, which says that clock skew is constant from cycle to cycle. This is not true for clock jitter. It varies from cycle to cycle. Clock skew, there is no change in frequency or period, which is again not true for clock jitter because it varies the period of my signal. In simple words, clock skew is nothing but a difference in the clock received between two receiving points on your chip, and we say that the variation in the phase happens but there's no variation in frequency or period. Now, sources of clock skew, one or two I have just mentioned here. One is the interconnect variation. We already saw that, the length of the wire. We also saw buffers present. Other one could be environmental variations like temperature and power supply, and so on and so forth. So clock skew also is a very serious problem, which we will see how to minimize in the future clips. Hope you have followed. Stay tuned and thank you very much.